My name is Oliver, and I work in the numerics group. So I've been working on NDSolve mostly, and I'm the person that's responsible for implementing the finite element method in NDSolve. So if you have seen a previous talk of mine, that's probably the old summary that I've used to conclude my talk with. So we have real and complex value, linear variable coefficients, PDEs with events. We can do stationary, transient, or eigensystem analyses of arbitrary regions in 1, 2, and 3 dimensions, and we can do that in parallel. So the last 1.5 years I spent with eliminating one word on this slide. I wanted to get rid of the linear, and that's what this talk is about. So I'm talking about nonlinear partial differential equations. So to recap a bit of what we can do, the first equation is basically the only equation we can solve with the finite element framework in Mathematica. So every equation you enter will be mapped to this first top equation. So for example, if you want to model something like a Laplacian equation, all these coefficients, m, d, alpha, beta, are 0, and only the c is set to 1, so that this models a Laplacian type of equation. So this is kind of a Lego for PDEs, and that's how this framework works. Now, these coefficients, you could have them depend on time or space, the capital X here. Now, in this version, in the upcoming version 12, they can depend on the dependent variable u and the derivative of the dependent variable u. So that's what's new in this in the upcoming version. The only exception to that is that m and d, so the transient coefficients, they only can depend on the spatial coordinates, but not on time and dependent variables. So they are linear, essentially. Right. So we'll start with a simple example. So what we have here is an equation that you can use to model minimal surfaces. So what we see here is a diffusion type of equation that has a nonlinear diffusion coefficient. So we have the derivative of the dependent variable is a coefficient to the equation, and that makes this equation nonlinear. So in the second row, I've written it down how it looks like in Mathematica if you type it out. And the third row shows the actual call to NDSolve. We call NDSolve value the equation. You give a Dirichlet condition of the dependent variable on u and specify that the dependent variable is u and the region is a disk. So this looks exactly the same way as before. There is no change in how you enter these equations or anything like that. It will return you an interpolating function, and then you can plot it. That's just roughly the outline. So basically, there's no change in syntax or anything like that to do nonlinear PDEs over regions. Okay, so to understand how this works, we'll quickly review Newton's method and what's implemented in FineRoot. So assume we have a nonlinear function g, and that nonlinear function has an unknown solution, which we call x star, and that's set to 0. I mean, that's the definition of the nonlinear function. So if we now say that we have x star minus an initial guess x0, there's a difference between the two, and that's a residual or a perturbation if you want to. So if we then say g of x star is g of x0 plus r0, it's just rewriting the equation. We Taylor expand this expression, so we have g of x star equals to g of x0 plus r equals to g of x0 plus g prime of x0 times r plus higher order terms. Now we get rid of those higher order terms. We just say we don't care about those. And we rewrite the equation. So g prime of x0 times r is roughly minus g of x0. And then we can rearrange the equation and start to make an iterative process out of it. So x1 minus x0 is about r0. And that's minus g x0 divided by g prime of x0. And from that, you can gain an iterative process. The only thing I've only added is now this lambda. This is a damping coefficient. This damping coefficient is larger than 0 and less than equal to 1. That helps to find the nonlinear root finder to find the roots. So just very roughly of how a nonlinear Newton method solver works. So this x0 is something that's an initial guess, a starting value, a seed, basically. And the equation we had before, this initial seeding was automatically set to 0. That's an arbitrary decision. If you want to change that seed to be something else, you can specify a new option called initial seeding. And then you say the dependent variable u of x equals 1. So now I've changed the seeding to 1 and not to be 0. Okay, that's just how you change the initial seeding. All right. So the first thing we had to do to implement nonlinear finite elements, we had to revisit find root. Now, find root has a Newton method implemented, and it works very well. The only thing is that the find root implemented Newton method is not optimal for large-scale Jacobian evaluations, and we'll see about what that's about. So I've written a small function, monitored find root, that gets some arguments and the Jacobian. And it calls find root itself. It monitors how many steps are taken, how many elevation it takes, and how often the Jacobian needs to be evaluated, and gives an output of that. Then we have a small differential equation, which I've discretized manually with like a finite difference approach, and I've written that down here. So we have a sparse array that's 1,000 by 1,000. G is then encoded in n squared a dot x plus x minus x squared, basically the equation we have there. I've manually written down the Jacobian, and I'm starting with an x0 with a constant array of 0. So if we look at how this looks with a standard find root method, we see that it takes 3 steps. It has 4 function evaluations and 3 Jacobian evaluations. All right. We've implemented a new method, and that method is called AffineCovariantNewton, and that is optimal in the sense that it uses less Jacobian evaluations. So it uses more steps, it uses more function evaluations, but it only needs 1 Jacobian evaluation for this specific problem. There's a set of several clever tricks how that algorithm does that. One of these tricks is something called Broyden updates. And Broyden updates are a mechanism in the algorithm to monitor the quality of the Jacobian. So it understands how good the Jacobian is and continues to use an outdated Jacobi as long as it can. If it finds that the Jacobian is too bad, it starts to recompute the Jacobian and then uses that newly computed Jacobian. Okay, what does that mean? So again, we're looking at the minimal surface problem we had before, and we monitor the steps evaluations for that nonlinear problem. And in this case, we see that NDSolve needed 20 steps, 22 function evaluations, and 6 Jacobian evaluations with a AffineCovariantNewton method. If we look at the original Newton method implemented in Mathematica, that uses 17 steps, 227 Jacobian function evaluations, and 18 Jacobian evaluations. And that makes up the time difference. So we see that the AffineCovariantNewton method uses 0.3 seconds, and the standard find root method uses 1.7 seconds to compute that solution. So this new method is beneficial if you know that you have a Jacobian, or if the Jacobian is expensive to compute and to use. So that's a new way to compute nonlinear problems with find root, and that's what's used inside NDSolve now as well. All right. So here's the same example, the find minimal example. On the left-hand side, we see the damping factors. That's the lambda. It starts with a 0.01, stays there, improves to the value increases a bit. So we get to 1. So it goes to 1, but here, then it starts to use the Broyden updates, has a few steps where it uses them, then finds, no, this Broyden is no good any longer, so I'll recompute the Jacobian, and then continues to use that newly recomputed Jacobian. That's how that algorithm saves time in solving nonlinear problems. Okay, I quickly want to talk a bit about the scope. What type of problems can we solve? So here's a nonlinear diffusion equation. In this case, we have the diffusion coefficient is u squared. That's one thing you can solve. We've already seen something like this. Here we have a derivative of a nonlinear coefficient. du dx is a nonlinear coefficient. And one thing that you should pay attention to is that if you directly use this type of equation, it will evaluate, of course. So now you have minus 2u prime, u prime prime. And that's actually not the equation you wanted to model. So what you have to do is you have to actually use the inactive term here to avoid that this is prematurely evaluated and that NDSolve actually understands that you want to model this equation. Right. Okay. We have nonlinear convection problems. So in this equation, we have a nonlinear convection term, 2 times u du dx. See that? We can have complex value nonlinear reaction terms as well. So here's a I times u squared. That's a nonlinear term. We have nonlinear load. So here's the sine of u. It's possible things like that. We can have nonlinear boundary conditions. So Neumann conditions can depend on the dependent variable in nonlinear ways. That's usually useful for radiation type of boundary conditions. We can have these nonlinear Robin boundary conditions on curved boundaries. So this is a coupled system. And in this coupling system, in this coupling of the system, so the dependent variable here is u to the power of 4. Yeah, so that's also something you can do. So you can also look at the... so that's the solution for this specific example. We don't have nonlinear Dirichlet conditions. And the reason for that is that you can always rewrite them as a linear, in a linear version. We're not 100% sure yet if that's really the right way. Right now I believe we don't need nonlinear Dirichlet conditions. If problems come up where we do need them, that's something we can still implement. But right now I think it's not necessary to have those. All right, so let's look at a few application examples. The first example I want to talk about is magnetostatics. So in this case, it's again a diffusion type of problem. And in nonlinear magnetostatics, you typically have several materials. You have iron, you have air, and you have coils and things like that. And they all have different permeability. The permeability depends on the space, where in the region of the object you are. And certain materials depend on the magnetic field. So in this case, the permeability depends on the derivative of the magnetic field. That's here. And typically, these materials have material data given to you by the manufacturer. And these data are called BH data. So it's a relation between the B field and the H field, and that's the permeability. And this is a plot of such a data. I've made a fit of that data. To use that fit in the coefficient. So this is the actual device I want to model. In gray, we see the stator. In red is the rotator, and in blue is air. And the color, the orange, white, and yellow are the coils around the fingers. That's the equation we're going to use. Right. So we see that the gradient of u squared, the total of it, and the square root of it is the norm of the B field. We have the permeability of air. Here is the fit, and the fit gets as an argument the nonlinear function. The element markers pick out certain regions. So this is the stator, and the rotor is marker 2 and marker 3. And the yellow and the orange coils will have a positive and a negative current flowing through them. And then you'll get a visualization of the magnetic field and the vector field in that device. Right there. All right. So Navier-Stokes equation. So this is a Navier-Stokes equation in the stationary case. The special thing about the Navier-Stokes equation is that in the first equation, it's a vector-valued equation. In the first equation, the pressure P is only available in a gradient form, and the derivative is not, or the P is not present in the second part of the equation. So yeah, that makes it hard to solve. So what we have here is, imagine a rectangular box that's filled with water. On top of the box, we have a conveyor belt moving the water in the right-hand side, on the right-hand side, and that the rest of the velocity field on the boundary is set to 0. We have a pressure boundary condition in the lower left-hand corner, and then and that's the flow field that develops in this box. So I have a second example. That's a backward-facing step. On the top left, we have an inflow profile. the velocity is given, so that's how the fluid enters this backward-facing step. On the right-hand side, there is a outlet boundary condition, so that's where the pressure is set to 0. These are the Dirichlet conditions that we use for this specific example. And if we So this is the flow profile then. Note that in the options here, I've given an interpolation order for U, V, and P. So U and V are the velocity fields. They are interpolated on second order, and the pressure is first order interpolated. And that's, if you are into finite elements, that's basically our way to specify that it should use a Taylor-Hood element. Yeah, so there are different ways of, different order of approximation are used for those. Note that there's like a recirculation area in this case, and the lower picture here is the pressure distribution over this backward-facing step. Right. Okay. What we've seen until now are stationary problems. We can also solve nonlinear problems in the transient nonlinear problems. And the first few examples is something you could do with NDSolve already because they are 1D in space and 1D time. And then I'll show you some examples about with arbitrary regions. So this first one is a post from Stack Exchange. So we have a nonlinear equation, and the customer wanted to, let's go back. The customer wanted to model an annulus that has two different liquids with different density. That's the initial distribution of the liquid, and they wanted to know how this liquid is going to behave in the field of gravity. So we'll look at that. So that's how the liquid is going out and flattening out. So that's a nonlinear problem, and that's something you can do with the finite element method now. Right. So here's an example of a Burgers equation. So this is a nonlinear convective equation. Yeah, it's basically you'll just enter it. It should work out of the box, and you can look at the result for this specific equation. So there it goes. That's how the solution for that equation looks like. Laundau-Ginzbug equation, that's usually if you find stuff that's written up in Landau-Lifshitz, you get a bit nervous. So this is a coupled system of equations. Again, this is something you can do already now with a tensor product grid method, like the standard method for NDSolve so far. I mean, the exact details of the equation are not too important now. I just wanted to show some pictures, some kind of a scope of what you can do. That's the solution for this type of problem. Okay, here's a Gray-Scott type of system. That's from chemical engineering. That's again a coupled system of two different concentrations, and that's used for that's how patterns develop on objects or on the skin of animals and things like that. I'm not going to go too much into the detail. I'm just going to show you maybe the result there. So this is the initial. So, and this is something you couldn't have done before because this is now a circular domain. So this is initial distribution of some concentration in yellow, and the blue is the region. And this is how the concentration actually develops during the time propagation. So that's also another area you can do now, right? Yeah, transient Navier-Stokes. So now same Navier-Stokes equation as before. Now stuff is time dependent. What we have here is right. So this is an inflow box. So the box, for some reason, it should extend further to around here. So the cylinder here is slightly off central, and it should actually it's more in the middle of the box. I don't know. And there's an inflow profile coming from the left. So the flow is surrounding the cylinder. We're going to ramp up this inflow profile with this type of ramp. So after about 2 seconds, the inflow is going to slowly come up. Right. Right, so there's a complete picture actually also. So let me just quickly show how it looks like. So what you're going to see now is the velocity profile, how the velocity in the x direction looks like after it has circled the cylinder, and you see that a vortex is actually starting up. So that's another. Oh yeah, thank you. That's. I mean, this is probably a standard test example for Navier-Stokes. So that's yeah, that works too. Right. Okay, let's move on. So because this is I mean, now we have this toolbox of PDEs that we can click, or not click, but that we can move or combine together. We just add another equation. So we add a heat equation now. So what's happening now is the Navier-Stokes equation is getting the temperature is fed back into the Navier-Stokes equation, and the velocity is driving the gradient of the temperature. With this, you can do something like a buoyancy-driven flow. So you have temperature, the temperature is driving the liquid in a certain area. Did anyone tell Apple they make horrible devices? I don't believe this. All right, okay. So at the lower left, there is a temperature that's hotter than on the top. So the temperature is going to rise and it's going to move the fluid. Oh, no. No. Ah, got that. So that's how. So note that actually the temperature, that's the visualization of the temperature, and it's actually oscillating. So that's one thing. Right. So since I'm pretty sure. So we can now do nonlinear valued variable coefficients. The thing that's remaining linear is the eigensystems, but everything else can be nonlinear. So if you allow me one more second, I'd like to point you to finite element add-ons. That's basically customer contributed additions to the finite element method. It has a structured measure in 2D and 3D. It has a smoother for meshes. You can convert quadrilateral triangles to quad elements, smoothing, and it has a domain decomposition solver. So if you have a cluster, you can start several kernels on a distributed system, and you call that function, and it will distribute the PDE onto the kernels, compute it there, and bring the result back. And I think, yeah, that's a picture of a domain decomposition. So yeah, thank you. That's it.